of what Bayesian networks are and what sorts of things you can use them for. There's two main components to Bayesian networks. The first one of these is representational, and the key thing to keep in mind there is that they provide you with a very general way of expressing probability distributions over random variables. The way they do this is graphically, and you specify a directed acyclic graph in which the nodes represent variables, the variables that you want to talk about a probability distribution over, and the arcs in the graph represent conditioning relationships.
How do we close the door here?
The second component of Bayesian networks is a set of very general algorithms that allow you to do EM, compute data probability, and to do Viterbi decodings, or the analog of Viterbi decodings. And these algorithms are parameterized on the BayesNet graph structure that you're working with, so that once you've written them, you can use the same code to study a lot of different probabilistic models. So here's an example of a relatively simple BayesNet. The variables are the nodes in the graph. And the first thing that you see is that there's two kinds of variables. One kind are shaded variables, which are, the shading means that they have observed values. You know what their value is. And the second kind of variable are unshaded variables, which are hidden. You don't know what their values are. In this graph, the observation variables all happen to be at the bottom, but that's not a general requirement. It just turned out that way. The arcs in the graph specify conditioning relationships, and in that way a factorization of the joint probability distribution. So the joint distribution, probability of A, B, C, D, and E having some particular values, you can read off how that's factorized from the topological ordering of the variables in the graph. So A doesn't have any parents, which means that you have a prior on A. B has A as its parent in the graph, so you have the probability of B given A. C has A as a parent, so you've got C given A. If you were just using the chain rule, then you'd have the probability of C given A and B, but the graph specifies that, in fact, you can ignore the probability of B in conditioning for C. Then D has B and C as parents, so you have this, and finally you have the probability of E given C. So associated with the graph, with the nodes in the graph actually, you have functions that allow you to look up these conditional probabilities so that you can then multiply them together and get whatever particular joint probability you want. You have to be able to look up, okay, well, if D has some variable value, little d, and B and C's values are these, what is the probability of D given B and C? You have some function in there that lets you look it up. Those functions can either be tabular or Gaussians. So I'd like to continue here by showing how you can express hidden Markov models as Bayesian networks, and then how you can extend that kind of formulation to look at phenomena that are interesting from the point of view of speech recognition. So up on the top there, you have a very simple HMM model. It's a 5-state model of the word digit. The nodes rather represent states, and the arcs represent, well, the solid arcs represent transitions and have transition probabilities associated with them. The dotted lines represent emission probabilities. The two shaded nodes here are just dummy initial and final states. So when you get an actual utterance and you want to reason about that utterance with an HMM, you need to make reference to a computational grid that's extremely specific about time. So suppose you have a 7-frame utterance that you know is a word digit, and you want to reason about that. You come up with a grid like this that specifies, okay, at time 1 I was in such and such a state, and time 2 I was in such and such a state. And you reason about specific paths through that grid, and then when you want to compute the probability of an observation sequence, you sum over all the possible paths through the grid. A Bayes-net representation of the same thing combines both the HMM topology and this sort of time-specific grid into a single structure. The way to think about it is at each frame in time, you need to identify a set of variables that you want to keep track of. And then across time, you specify how those variables evolve. So in order to represent the same information that's in the HMM, the set of variables that you need to work with are a state variable that tells you what state, whose value tells you what state you're in at any particular time, and an acoustic observation variable whose value just tells you what the acoustic was. The assignment of values to the state variables here corresponds to this path through the network. So the state at time 1 was the state at time 2 was state at time 3 was okay, and that corresponds to this, and so forth. In the same way with the HMM, that you need to sum over all possible paths through the HMM to compute things like the observation probability. With the Bayes-net, you need to sum over all the possible ways that you can assign values to the hidden variables. You encode the transition probabilities in the conditional probabilities associated with the state variables, so that, for example, you could look up the probability of an following a d, and that would correspond to the transition probability on the arc up there. And you encode the emission probabilities within the observation variables. The factorization of the joint distribution that you have reading off the graph is, well, the probability of the state at time 1 being a d times the probability of the first observation given a d times the probability of an given a d, and so forth. And that's what you get from an HMM. Okay, now there's a couple of problems with this simple picture that make it so that you have to do something a little bit more complicated actually to work with these. The first thing is there's nothing to prevent, when you do inference and sum over all the possible ways that you can assign values to the hidden variables, there's nothing to prevent you from assigning all the way down the line, so you just have a long sequence of does. When you multiply together the probabilities, you'll get something that's not 0, but at the same time it doesn't correspond to a path through that HMM up there. So you're not capturing the constraint that you've got to start at the initial state and end at the final state. Another problem with this picture is that if you look at the transition probabilities, the probability of a j following an has to be non-zero here, or I. On the other hand, that probability does have to be 0 for this occurrence of I. Okay, because you don't want to have ija, 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 ija. You need one ija and then one it. So there's a couple of problems with that simple picture. And you can solve those problems by using a little bit more complicated of a structure, something that looks like this. So what's going on in this picture is that we're now making a distinction between the position in the HMM graph and the phone label associated with that position. So what we have up here is a set of variables that say for each point in time, what state, what position in the HMM are you in? And then down here a set of variables that tells you what is the phone that labels that state. Also, there's a transition variable here. When the transition variable has a value of 1, you set up the conditional probabilities so that the probability of this having a value 1 greater than its parent's probability is 1, and the probability of anything else is 0. That ensures that you go into sequence position 1, position 2, position 3. Set up the prior on that first state so that the probability of time 0 being in state 1 is 1, or in being in position 1 is 1. And then you have deterministic mappings that you set up for each word model that tell you, okay, if I'm in position 5, that's phone 2. The way that you ensure that assignments of values that don't end up in the final state get 0 probability is that you add a dummy end of word observation variable here with just an arbitrary value of, say, 1, and you set the conditional probability of seeing a 1 here, given that this value is anything but the last state in the word, you set that probability to 0. Now, it's often actually useful to insist on ending in a transition out of the final state of the word. So you can also condition on this transition variable at the last time step. Okay, so when you set up a network like this, you can then assign transition probabilities here and observation probabilities here in such a way that every assignment of values to the variables in the Bayes net corresponds to a single path through the HMM, and that the probabilities that you get for those assignments corresponds exactly to the probabilities that you have for those paths. That means that when you sum over all the possible ways of assigning values to the hidden variables, you get the same as the sum over HMM paths, so you can compute observation probability. And when you find the likeliest assignment of values to the hidden variables, that's the same as doing Viterbi decoding. And I just want to pause here for a moment to emphasize that there does exist a set of algorithms I'm going to talk about later that are parameterized on the structure of the Bayes net graph that allow you to do the things that you need to do for speech recognition. In particular, you can compute the probability of a bunch of observed values for variables. You can find the likeliest hidden variable values, and you can also do EM in order to find the conditional probabilities that maximize the probability of some data set. Okay, so now that we've set up a basic structure in which you can express the kind of information that you have in an HMM in a Bayes net format, we're ready to start generalizing and looking at new things. And so what I want to do here is just show how you can capture a variety of interesting phenomena in this formalism. So the first one is doing articulatory modeling. This is articulatory network. And what's going on here is that all of a sudden there's an extra layer of variables that's mediating between the phone and the acoustics. In this particular graph, there are two articulatory variables, a tongue variable and a lip variable. The person is saying the word no. This is just a representative assignment of values. The tongue starts out on the alveolar ridge, and the lips start out unrounded. And by the time the person is around to saying the O, the tongue is in the back of the mouth and the lips are rounded. The probability of the acoustic depends directly on the articulatory positions, and the probability of an articulator position depends both on what the person is trying to pronounce, and which captures linguistic information, and on its value at the previous time slice, which captures physical inertia. There's one other thing to recognize in this graph, which is that there are some conditional independence assertions in it, namely that not everything depends on everything else. The lip position depends on the previous lip position, but not on the previous tongue position in this graph. So what this kind of thing lets you do is capture things like feature spreading, asynchronous feature changes, that kind of thing. A more conventional kind of extension to HMMs that you can capture, developed here at Johns Hopkins, probabilistic state classification. The idea here is that on top of the basic HMM superstructure, you say, well, phones or states can actually map into cluster values. And the cluster that a state maps to is not going to be a deterministic thing. There's going to be some distribution. Associated with each state cluster is a set of Gaussians. And the Gaussian that you want to use in order to model a particular acoustic is determined by the value of this mixture component variable. So the combination of a cluster value and a mixture value tells you what Gaussian to use, and then you can compute the probability of the acoustic observation. So computing involves summing over the values, over the ways you can assign values to the things that you don't know. So in particular, if you want to know the probability of an acoustic given a state, so the acoustic given a state, you'd have to sum out over all the ways you could assign cluster values of, well, you've got the probability of the cluster given the state, and then you'd have to sum out over the ways that you can assign mixture values of the probability of the mixture component, using that mixture component given the cluster that you're in. And then finally, you have the likelihood of the acoustic given the cluster and the mixture.
I don't understand. The state does not belong to a state does not belong to a particular cluster. I mean, no, I'm sorry. But you have phone, and in parentheses you have state.
Right.
So I took that to be the state.
That right.
So
That's what I mean.
So that a state is in one cluster and only in one cluster, and therefore the transition will be with probability 1.
From state to state cluster?
Yes.
So this is the soft clustering where
Oh, this is our soft cluster.
this is our soft clustering. So it's actually
I see.
more than 1.
Uh-huh. Okay.
So then that's a variable.
That's what it was meant to
But
capture.
then there would be other connections to it. I mean, if I were to write a graph, there'd be other connections
Between what and what?
between states and the cluster.
No,
Because-
so that circle is basically a random variable. It has multiple hidden values, and so there are.
Okay, well, I won't interrupt you. I will interrupt you. I'll stop my interruption. That's what I do.
Okay. To model rate of speech, one thing that you might do is say, well, I think the probability of a transition depends on how fast a person is talking. And I don't really know how fast a person is talking, so what I'm going to do is I'm going to introduce a hidden variable that represents rate of speech. That's probably not going to change too much from frame to frame, so I'm going to condition the probability of the speech rate at the current time on what it was at the previous time. And I'm going to condition the probability of having a transition on both the phone and on the rate of speech. And if you wanted to, you could do something fancier. If you had an acoustic observation that you thought was particularly indicative of rate of speech, you could add in that acoustic observation down there and then condition this hidden variable on that actual observation. Another model that you can express in this format is parallel model combination. And the idea here is that up on top, you've got a standard HMM that is producing a acoustic stream that's uncorrupted speech, pure utterance. At the bottom, you've got a noise HMM that's also running and producing a stream of noise, uncorrupted noise. What you actually observe is an acoustic observation that depends both on the clean speech that the person produced and on the noise that was present. These things aren't restricted to acoustic modeling type phenomena. You can also express many different language modeling phenomena in terms of Bayes nets. And so here we have a trigram language model expressed as a Bayes net. We've got the sequence of words, and the joint distribution over word sequences is factored as the probability of word I given word I minus 1 and word I minus 2. You can get a little fancier if you want and model, have a class-based trigram model where you assume that you have an underlying hidden sequence that represents the part of speech of the word. The part of speech depends on the previous parts of speech, and then the word itself is conditioned on the part of speech, so you have some distribution over words given that you had an adjective or determiner or something like that. Okay. So I'm gonna change now to talking about the algorithms that you use to compute with these things. So let me just pause and see if there are points that people want to bring up about the structures.
I have a question.
Yeah.
In a lot of these drawings, if you put up the last time that you had, there are actually 4 hidden variables in here.
Right.
So in the algorithms that you're going to have later on, for instance, and also there are 4 observed variables, each of which depends on a corresponding hidden variable.
Yes.
To what extent do you need to assume that, for instance, the conditional distribution of word 1 given POS 1 is the same as or different from the conditional distribution of word 2 given POS 2? Is there like a stationarity or something?
Yes, the idea is that you have time invariant probabilities. That basically you have the first slice is unique, or the first couple of slices are unique, and then after that you get a repeating structure. And the desire is that the probabilities remain, the conditional probability should be the same in each time slice.
Okay, because otherwise I was puzzled by why in the very first slide you had 2 E's in the word digit, why you wanted to somehow make them the first E and the second E the same, because by adding all these other fancy states on top.
Okay, so
because if you have a invariant thing, you could very well say that the transition probability in this one, you could very well say that the transition probability is in some of those states.
Right, exactly. Exactly. If you weren't insisting that the conditional probabilities be the same in every time slice, then it would not be a problem to say, well, if you're dealing with the second then you can go to a t.
Okay. So, but you want them to be the same, that's why you had that.
Right. Yes. Yes, thank you. All right.
If you want to use the net, say you want to model that, you say you did want to keep track of time that you spent in the state, and you did that in a regular range map, your state space would actually be quite large. So, because you would make it a dummy state space by indexing your state file and how long you were in it. So you must be specifically trying to avoid that. That would be that problem.
Right. You'd have the same problem here if you were if you wanted to count the number of times that you were in a state, or if it was the first occurrence or the second occurrence of a particular phone or something like that.
And I get confused by when you put the black circles up, are those
The black circles represent variables whose value you always know. So in the HMM pictures, those represent the speech frames. If you have a particular utterance that you're dealing with, you've always got the acoustics sitting in front of you. So there's nothing hidden that you have to sum over there. Okay, the key to doing inference with Bayes nets is to use dynamic programming in a manner that's analogous to the way in which it's used with hidden Markov models. With HMMs, the key point is that a single frame divides everything you know about the past from everything you know about the future. And so you can compute probabilities up to a single point, and then probabilities conditioned on particular values for that point, and combine those. The Bayes-net algorithms are defined in terms of tree-structured Bayes nets. Now, the graphs that I showed before were not tree-structured. I'm going to show how to turn those graphs into tree-structured ones. But assuming that you have a tree-structured Bayes net, then you have something that's exactly analogous to the hidden Markov model case. In that case, any particular variable, xi, separates the graph into two disjoint parts: the set of variables rooted in it and the set of variables not rooted in it. I'm going to refer to the facts that we know about variables as evidence. What we know about xi I'll refer to as e sub I 0. What we know about the variables above xi, its parent and its siblings, I'll refer to as e sub I plus. And what we know about the variables rooted in xi, I'll refer to as e sub I minus.
Actually, what distinguishes, why is xi of particular interest? Is that the observable? No.
No.
What is xi?
Okay, so
here?
so if you're doing inference with an HMM, you define
Inference of probability.
right.
Yes.
You define the alpha probability as the probability of everything you know up to and including a particular frame.
Right.
Now, you're not talking about any particular frame there. You actually do it for every frame in order. So it's going to be the same here. xi separates the graph. And in fact, every variable separates the graph in the same sense that every time frame separates an HMM into two parts. So I'm just focusing on one for the definition of the recursions. So we're going to define a quantity, pi super I sub j, as the probability of everything we know about these variables above it, all the observations we have about the variables above it, and xi having a particular value j. And that's analogous to the alpha probability. Lambda ij is a probability of everything we know about the variables rooted in xi and about xi itself, given a particular value for xi. So what that means is that the probability of all the evidence and xi having a particular value j is given by the product of these two quantities. It also means that if you want the probability of the evidence or the observation stream, that all you have to do is sum out over all the possible values for xi. And if you want the conditional probability of xi having a particular value, given the evidence, you have that ratio. So, and then again, these quantities are defined for each variable. The recursions that you get are these. You end up doing a bottom-up pass, a post-order traversal of the tree, and you compute the pi ij's. The formula for computing them, aside from the base case where at the bottom you have a 1, is this. And, well, I'm not going to go into it. the thing to note is that the place that you take the evidence into account is when you compute the lambda ij, you have some value unless the value j for a variable xi is inconsistent with what you know about xi, in which case you just set it to 0. The top-down recursion,
lambda ij refers to what? That's the backward.
that's a backward, right?
That's the beta.
Right, that's the probability of everything below and what you know about xi given a particular value. Top down, the recursion is this. You sum over all the possible values that the parent could take of the probability of xi having its imputed value given that the parent has that value times the probability of everything not rooted in the parent. And then you also have to take into account what you know about these siblings, which you do over here. And the evidence comes into play here in the sum where you only sum over the values that are consistent with what you know about the parent. So the thing to take away from these recursions is that they're actually relatively simple, and that if you had a tree-structured graph, it would be relatively straightforward to write the program that actually computes those recursions and then combine them in the same way that you combine alphas and betas. The extension to Viterbi computations is pretty straightforward. I'm just sticking a star up there to indicate for the lambdas the probability of the likeliest values of the variables rooted in xi as opposed to the sum over all the possible values. And the recursion, which is this. And for the pi's, we want to find the probability of the likeliest set of variable assignments for all the other variables. And then in the recursions, you end up replacing sums with maxes, and you can set up the bookkeeping to do back traces, essentially, and keep track of what the likeliest variable values were. There's one fine point that I want to just mention, which has to do with doing online decoding. And the problem there is that in those recursions, the pi's, the things that you compute top-down, were actually computed in terms of lambdas. There were lambda quantities in there. And what that means is you've got to do the backwards pass before you can do the forwards pass, which is fatal for doing online decoding. In fact, there's a couple of solutions to that. And the first one is that if your graph structure is even simpler than a tree, if it's just a chain, then it turns out that the dependence of the pi's on the lambdas goes away. And the second solution is to actually interleave in a clever way the lambda and pi computations so that you never need to work with something that you don't have. If you have a chain-structured graph, then the recursions become very simple. The probability of everything below here, given a variable value here, is you just sum over all these possible values. Probability of everything below this one, given the value for this one, times the probability of this guy's value given the value over here, which is this. And the pi's, probability of everything up to and including xi is the sum over all the ways you can assign values to this one of the probability of everything up to and including this one times the probability of this one given that one, which is this, and it doesn't have any lambdas in it. So you can compute that top down and you don't have a problem.
Your earlier example was each one of those states was a particular value at the time.
Right.
So you're really interested in states of multiple times, right?
I'll get to actually making chains, and you can do it. Okay, so the more complicated thing that I just want to mention in passing is something I call backbone decoding. And the idea here is that if you have a repeating structure, to find a backbone through it. So in this case, the horizontal line here. Okay. Then the idea is to compute the lambdas bottom up on the side chains, and the pi's only top down on the central chain. So suppose you've got the lambdas for the side chains, and the pi's up to here. How would you compute the pi for this one? Well, the pi for this one is actually a function of the pi for its parent and the lambdas for its siblings. And that's what you have available. So you can get the pi for this one. Then you can start down here and back up the lambdas, and back up this, well, this one is just a base case, and get a lambda for this one. And then you're ready to go on because you have the pi for the parent and the lambda for the siblings. And then in the backwards pass, you need to compute the lambdas for the backbone, which you can do because you're just going bottom up. And then you need to compute the pi's for the side chains, which you can do because at the time that it comes to compute the pi's for the side chains, you have the pi for the parent, and you have the lambdas for the siblings. You got the lambdas for the siblings on the top-down pass in the first place. Okay, so anyway, the point of that is just that if you want to be clever, you can in fact take the tree-structured graph and do computations directly on it. You don't need a chain-structured graph.
That graph is essentially chain-structured because anything that's not a chain ends very quickly.
That's the key to proving that this sort of thing works. And you can prove that for a wide variety of Bayesian graphs that are not chain structured, that are general structured, that have loops in them, that when you go through the process of converting them into chain structured graphs, that in fact it's impossible for them ever to have long side chains hanging off. Okay, so now we come to the last key in the process of doing inference with these things, which is that if you don't have something that's structured as a chain or a tree in the first place, what do you do with it? And the answer is that you do essentially what amounts to a change of variables, where you construct a new set of variables. Each of these new variables represents a subset of the old variables. And then you structure these new variables together into a tree and assign conditional probabilities in that tree structure in such a way that you get a one-to-one mapping between assignments of values to the variables in the new representation and assignments of values to the variables in the old representation. The subsets of the old variables are referred to in the literature as cliques, and there's two requirements, it turns out, for the new representation to be the same as the original general Bayesian representation. And that is that each variable in the old representation has to occur in at least one of the new variables with its parents in the old representation. That's the first requirement. Second requirement is that, yes?
Parents and the variable have to be in the same clique.
Right. The second requirement,
Parents means immediate parents.
right, the immediate predecessors in the graph, the things that it's conditioned on.
Yeah.
The second requirement is that if the same old variable occurs in more than one clique in this new representation, then it has to occur in every clique connecting those two cliques. It has to occur consecutively in cliques. So a couple of examples of that. Here's the graph that we started with. It's got A, B, C, and D. It's a graph of variables. Here's a tree of cliques. This first new variable represents the variables A, B, C chunked together, And the values that this variable can take are the Cartesian product of the values of A, B, and C. Here's B, C, and D. Here's C and E, B, and C. So that is the first requirement met. A doesn't have any parents, so that's easy. B has A as a parent, so there's A and B together. C has A as a parent, so there's A and C together. D has B and C as parents, so there's D, B, and C. E has C as a parent, so there's C and E. Well, we didn't really need this one for anything, but that doesn't matter. In fact, it can sometimes be good in terms of computational speed to add extra variables that contain the intersection of the variables in adjacent cliques, and that's what this is for. That's just purely computational. It doesn't matter. And then if you pick two cliques that contain a variable, so say C, this one has C and this one has C, and you look at all the cliques along the path connecting them, that's got a C also. Or if you take this one that has C and that one that has C, C is there. Or if you take B, so that it occurs always adjacently. So how do you get the probabilities in these two representations to be exactly the same? Well, the first thing to realize is that assignment of variables.
First thing to realize.
How do you get the probability of two joint assignments of values to the variables in the two different representations to give you exactly the same number so that you can set up a one-to-one mapping between assignments of variable values in the two representations? And the first thing to realize is that if you have an assignment of values to the variables in this representation, that corresponds exactly to an assignment of values to the variables in this representation. Now, assignments of values in this representation, it almost goes backwards. There's two cases. Either you have a consistent assignment of values, in which case it fixes an assignment of values over here, or there's an inconsistency, like in the assignment of values to this variable, there's an underlying assignment to B that's, say, 0, whereas in the assignment of a value to this variable, B gets a value of 1. That's an inconsistency.
So there's
Yep.
conditions where to ensure that this mapping is 1-to-1.
We want to get a one-to-one mapping going on here, yeah. And the way we do that is that in the conditional probabilities, the first thing we do is that the probability of this having a value that implies an inconsistency with a shared variable in its parent, we're going to set that to 0. There can't be inconsistencies. And that's the root of the second requirement that two occurrences of a single variable have to be on every path along, have to be in every clique along the path connecting them. Okay, the second thing we're going to do is we're going to go and we're going to take the probability in the first representation, the conditional probability in the first representation, and we're going to stick it over in the clique that contains that variable and its parent. So in particular, we're going to assign, in this case, A to this clique, B to this clique, and C to this clique. We're going to combine E to this clique, assign E to this clique, and D to this clique. So you assign each variable to the clique that occurs with its parent. And then you set up the conditional probability of that clique as the product of all the of the conditional probabilities of all the variables that have been assigned to it. So the prior probability of this clique having a particular value is given by the product of the prior on A in that representation, the probability of B given A from that representation, and the probability of C given A in that representation. And you have all those quantities available. You know what A, B, and C are because their parents are right with them. Okay, and then so for example down here, the probability of this having a particular value given its parent's value is either going to be the probability of D given values for B and C, or 0 if it implies an inconsistency for one of these shared variables, B and C. So when you set things up like that, when you finally go through and multiply together all the conditional probabilities for a specific assignment of values to the variables, you get exactly the same number out in the two different representations, which means that when you sum over hidden variable values, you get the same answer, and when you max over variable values, you get the same answer.
Is that probability, is that a joint or is it a sum? Should it be P of A E plus P of A C?
It's a product. Yes. Assume that you have a specific assignment of values over here. Okay, then the probability of that joint assignment is probability of A times the probability of B given A times the probability of C given A times D given B and C times E given C. Now suppose you've got a specific assignment of values over here. The probability of that concrete instantiation is what we've assigned up here, which is these three factors, times what we assign over here, which is either 1 if we have a consistency between B and C, or 0, times what we have over here, times what we have over here. So when you multiply all these things together, you're multiplying together exactly the same numbers that you multiplied together over here. So you get the same answer out.
Except there you have C given E and over there you have E given C.
Oh, I miswrote that. That should be E given C.
The only drawback actually is that for computations, I mean, there appear to be many more configurations on the right than there are on the left, and then it's the probability which rule out many of them because there are zeros. So do you have to factor this when you?
It pays when you do the sums to keep track of the things that are in fact possible, and only to sum over the things that are possible. And that actually ends up being an easy thing to do.
Because in the beginning you said something about having generic software which does it.
Right.
If you did that, then that software would start looping over all values.
No, in fact, it's easy to write generic software that can immediately identify what things are possible and sum over them, and what things are impossible and just never even consider them. Yes?
This might be surprising at this point, but is there a notion of a measure of complexity? Because you could group everything in,
Yes.
one state.
Yes.
So you have a
The computational complexity for doing any of those algorithms that I mentioned is equal to the sum of all the possible clique values. And remember, the number of values that a clique can take is equal to the number of values that the cross product of the variables can take. So if you get a lot of variables in a clique, that's bad. And in fact, in general, inference with Bayes nets, any general purpose inference thing, is potentially exponential in time. And the reason for that is that it's possible to encode NP-hard problems as Bayes nets. So the stereotypical NP-hard problem is 3 satisfiability. You've got a bunch of variables, and they're connected together in disjunctions. Each disjunction is a disjunction over 3 variables. And then you look at the conjunction of all those disjunctions. And you say, is there assignment of values to the variables that satisfies this big expression? And the way you encode that with the Bayes net is you say, well, here's a bunch of true-false variables. And here I do the disjunction. So this is going to be true if this or this or this is true. And this is going to be true if this or this or this is true. And then down here you have a layer of AND variables. This one is only true if this and this is true. This one is only true if this and this is true. So this one down here is only true if absolutely everything is true. And then you say, I've had an observation. I've observed that this is true. What's the probability of that observation? And if the probability is not 0, you know that there's an assignment, a satisfying assignment. And you can be even more precise. You can say, well, here's my observation. What's the Viterbi decoding of it? What's the likeliest assignment of values? So in general, you have problems, or you can have problems. In fact, for a very wide variety of graph structures, and all the graph structures that are relevant to speech recognition, you don't run into this problem.
So you mentioned that the state space blows up.
Can blow up.
But that, according to the previous graph, that's not strictly true because many of the assignments in the lower cells were ruled out by the assignment in the first cell.
Right, but
the way you flow down the graph. So
in general, that doesn't save you. No.
computational complexity can be harder than the graph on the left. When you have on the previous graph. When you have
Right, no, you're right. Right, but the point is that if you take a graph like this, the computational complexity of solving this graph here, or answering the queries about this graph here, those are exponential time. Because in fact, answering those queries solves NP-hard problems. Yeah?
What happens to the distinction between hidden and observed variables once you go through the transformation to a tree structure?
Okay. That's a good question. And the answer is nothing happens with one little itty-bitty exception. The notion of the set of variable values that are consistent with what we know about a variable xi. Before the set of variable values that was consistent with what we know about xi is either the single value that we've observed for xi or any of the possible values for xi, because it's either observed or not. Now, in one of these cliques, you can have some observed variables and hidden variables mixed together, and the set of consistent values is just a set of values that's not ruled out by any of the constituent variables, any of the constituent evidence variables. So everything remains exactly the same. You just have to watch out for that, what's consistent. Okay, well, I am running short on time here. So I think what I'm going to do is just present a very simple algorithm for producing chains. I'll skip the algorithm for taking a general graph and turning it into a tree, and then I'll finish up. So there is a very simple algorithm for producing clique chains that satisfy those two requirements for equivalency. And in fact, they're practical if you want to do speech recognition. And the idea is to maintain a single frontier clique. And then at each step, you generate a new clique to make its child. And the way you do that is you look at the clique, the frontier clique, and you say, are there any variables in it whose children have all been added, whose children are all present in the clique? And if the answer is yes, you throw it away, and that gets you your new clique. If the answer is no, you go off and you find a variable that either has no parents or whose parents are in the clique, are in the frontier, and you add that in.
I don't understand how throwing something away gives you something new.
So here's an example. We start out with an empty frontier, and a variable that has no parents is a, so we add it. Then we go and we add, we say, okay, is there a variable whose children have all been added? The answer is no. So is there a variable whose parents are all in the frontier? The answer is yes. B. So we add B, we have AB. Well, we still haven't added all of A's children, and we still haven't added all of B's children, so we can't do anything except add another variable. So we add C. So now we have ABC. Now we have, in fact, a variable in the frontier whose children are also all in the frontier. That's A. Both B and C are in the frontier. So we remove A, and we get this. So that's the nucleic. Okay, but B and C still have remaining children. So now we go off and we add one of those children. We add D. We have BCD. C still has a remaining child. D doesn't have any, so we could remove it. And B, all of its children have been added. And so we're going to pick on B, and we're going to remove B, and that gets us CD. C, as I said, has no children, so we can remove it. Now we're down to just C. Then we add E. We have CE. Then we can remove C, and then we can remove E. Why does this satisfy those two requirements that I mentioned before? First, each old variable has to occur in a single clique with its parents. Well, we only add a variable when all its parents are there. So we know that at the point that we add the variable, we've identified a clique that has a variable in its parents. So it satisfies the first requirement. Second requirement, that it occurred consecutively. Well, you add it at a given point, and then it remains in there for a while, and then you remove it, and you never add it back. So it's consecutive. If you do that with a hidden Markov model, you add the first state, and I'm reverting here to the simpler version of HMMs. You get the same thing if you use a more complicated one, or the compute time is the same. You add the first state variable, you have Q1, add the first observation, then you have Q1x1. Then you add, then you can, let's see, then you can remove x1 because it doesn't have any children. Then you can add Q2, you get Q1, Q2, and you proceed along like that. And if you look at the number of values the cliques have, since x is an observation, you don't really have to worry about it. This is just the size of the state space. And here, Q1 times Q2 is state times state, so that's basically the size of your transition table, which is what you get from an HMM. But I want to caution that it does not always pay if you have a structure, fancy structure like this, just to turn it into a simple structure like this. One thing you could do is you could say, look, I've just got a bunch of hidden states up here. So what I'm going to do is I'm going to make a single super variable that represents them all the hidden state in a particular time slice, and put it right here, and that's it. And then I have something that looks like that HMM picture, and I'm going to go off and do inference with it. That's actually a bad thing to do. And the way to see that is assume that each of these variables has, I don't know, n values. Then each state would have n to the fourth possible cross product values. And n to the fourth times n to the fourth is n to the eighth. On the other hand, if you use that frontier algorithm that I mentioned, you do an add, doesn't matter because it's just an observation, remove it. Okay, so now you're up to 4. Add this, you're up to 5 things you have to keep track of at once. But now this one has all its children added, so you can remove it, and you're down to 4. And then you can add this one. Okay, you're back up to 5, but now this has all its children added, so you can remove it, so you're down to 4 again. And if you work through it, it just oscillates between having 4 and 5 constituent variables in there. So the runtime is going to be n to the 5th instead of n to the 8th. Okay, I don't want to keep people late. So I'm not going to talk about trees in general. I just want to finish up by pointing out a couple of projects that would be outstanding research topics. And one of them would be to actually find a really simple database like the Wisconsin X-ray database and try to do some articulatory modeling And if you could get it just to identify articulatory positions for the simplest grunt, that would be fantastic. I have used these myself. I didn't talk about that work here to do speech recognition, but only with very simple extensions to HMMs. So doing something like this is, that would be a very interesting thing to do. A second topic that would be interesting to explore.
Are you that generous everywhere? Or only at Johns Hopkins?
Only here. Second area that would be very interesting to explore is to actually use these things for language modeling. So an example of, sort of a Gestalt type language model is, well, you've got some predictor set from which you want to predict what the current word is going to be. Then you see the current word. Then there's a function, and you're going to factor this as some kind of a probabilistic network, that takes what was the previous predictor set and what you've just seen and maps it into a new predictor set, and you keep going. And with those words, I think I want to finish, and if there's any questions, I'd be glad to take them. Yes?
I'm not sure I understand this whole idea of the frontier, but do you know ahead of time the exact, at each step, the exact nodes that will make up the frontier?
You can either pre-compute them, because if you have a repeating Bayes-net graph, then what happens is you start to get a repeating frontier sequence. Or you can just compute them dynamically using the rule that to get the next frontier, you look to see if there's any variable whose children are all present, and if there is such a variable, you remove it, and that gives you the next operation to do. And if there's not, you go off and find a variable that either has no parents or whose parents are already in the frontier, and you add that variable.
Okay, and now if you could compute the sequence of frontiers, why wouldn't that make the perfect leap? Maybe I don't understand what you're being said, but if you know if the frontier contains everything you need to know to compute the next frontier, is that right?
The frontier has a set of variables.
Yes, and that contains all the information you need to know to compute the next frontier. Is that true?
The combination, so the only thing we're computing are sets of variables. We're just making a tree of or a chain of variables. And with that understanding, yes, the current frontier has everything you need in order to generate the next frontier.
So why would you make like every frontier, like that sequence of frontiers, the clique?
Yes. The set of variables in the frontier at a particular time defines a clique. And the frontier that you get at, the tth frontier is a child of the t-1th frontier. Yes?
What is the history of this? This is in your PhD thesis or something? Is there big literature about this and any of the algorithms you mentioned, your algorithms?
So there's a couple of, I think there's a couple of background books that are available. One of them is by Judea Pearl. Another one is by a fellow named Lauritsen on graphical models.
This is a which is maybe 92.
Right. Right. The formulation that I've presented here is original to my thesis. That the idea of doing the change of variables and expressing things in those terms, and also the chain or the backbone decoding, where you do the interleaved lambda and pi computations.
So
Um,
It's computing the same thing.
let me see if I can find the appropriate slide. This one will do. If you just replace the sums with maxes, then that's the same as a Viterbi slide. And the difficulty arose because in this, if you have a tree structure, then you compute the lambdas like this, bottom up, and the things that you get top down are computed in terms of the lambdas that you get from the bottom up. So what that implies is that before you start doing the top down pass, you have to have done the bottom up pass. And that's the root of the difficulty. And that occurs because you have side chains on the tree. And if you just have a chain, that goes away, and the HMM turns into a chain. Was that the question?
That was the answer.
Okay.
So you were talking about a more general structure than what we know.
Right. Yes.